Hello, everyone, and welcome to the next lecture in our course Reasoning LLMs from Scratch. In the last lecture, we looked at an algorithm called Trust Region Policy Optimization. We started by looking at the performance measure of an objective of a policy, which we denoted by n of pi. Our entire goal uh, in TRPO is to find a policy which maximizes this performance measure. Now, the question is, how do we maximize the performance measure of this policy? Well, to do that, initially we looked at what if we have another policy pi dash whose performance measure is given by n of pi dash. Now, the question we asked is that can we write the performance of this new policy in terms of the performance of the old policy? And the reason we think of this approach is that if we are able to write n of pi dash in terms of n of pi, we will get some idea of in which direction should we make our updates so that it moves towards the direction of an optimal policy. So then we saw, okay, n of pi dash is the performance which I want to maximize, and it can be written as n of pi plus two parameters or two terms. First is the state distribution, and the second is summation over advantages. So, what we saw was to find the performance measure of the new policy, let the agent visit each and every state in the environment and let the agent choose an action based on the new policy. And then for every state the agent has visited, you calculate the advantages for every state and you sum all those advantages over. So now, this was our intuition and this is our true objective function which we want to maximize. So I am going to give a label of true over here. Next, what we looked at is it's hard for us to find the state distribution because the state distribution under the new policy is not known. So we thought of, okay, if the state distribution is not known, what can we do? And we looked at an interesting approach where we considered this function. Let me draw this function here right now. So let's say we consider this function whose maximum I want to find out. And I do not know this function. I do not have the expression for this function, where on the y-axis you have n of pi dash. Okay, and on the x-axis we have theta, which is the policy parameter. So what we do is, let's say we are somewhere here, which is obviously not the most optimal policy. We construct a surrogate function which is always less than the true objective function and which matches the objective function at one point. And then we calculate the maximum of that surrogate function. So we get the next point. Then we again calculate the surrogate function, find the maximum of the surrogate function. Then we get the next iteration. Then we do that and we gradually move towards theta, which maximizes our true objective function. Now, the main question is what is this surrogate objective function? And we looked at a very interesting expression for this surrogate objective function, which turns out to be L of pi dash minus C D K L max pi of pi dash, pi comma pi dash. The first term is exactly same as the true objective function, but with the state distribution calculated according to the old policy, and the second term measures the KL divergence between the old policy and the new policy. So it turns out that we can prove that this term is less than the true objective function, which is the true performance measure of the new policy, and we can see how it matches the objective function at exactly pi equal to pi dash. So for pi equal to pi dash, both the distributions are the same, and the KL divergence is going to be zero. And for pi equal to pi dash, the state distribution of the old policy equals the state distribution of the new policy. So this simply becomes n of pi dash. So this way we found a policy iteration algorithm which sequentially calculates a better and better and better policy. And we continue this till the point we reach the optimal policy. Now, towards the end of the last lecture, we also discussed how we can decompose this objective function into this, where we maximize only the first term and the second term is added as a constraint. So, this is called as the trust region, which is delta. And the trust region ensures that the new policy does not deviate much from the old policy. It always remains within the trust region of delta. Now the question is that how do we solve this constraint optimization problem? And we will look at that in this lecture, and it will the final expression will actually be very similar to the vanilla policy gradient the vanilla policy gradient expression which we were looking at in the previous two lectures before we started covering TRPO. So it would appear that why did we go through all these lengths to come up with that expression if it was so straightforward? And that was my reaction when I reached till the end. But oftentimes it happens that the most powerful expressions are simple when you reach towards the end of deriving those expressions, and you find out an intuitive way of coming to that expression through a simpler route. So we are going to look at that, how it can be related to policy gradient as well. Okay, so for now, the task for us in today's lecture is to solve this constrained optimization problem where we are given an objective function and we are given a constraint. So let's see how we can start this problem. First, we have to simplify this objective function which is there in the brackets of the maximize function. So let's expand this L old pi new. This expression looks like this as I had written over here. It's a combination of two terms. This is the state distribution according to the old policy, and this is the summation of all the advantages which the agent encounters for every single state. The intuition of why these advantages appear in the expression is that if the advantage is positive, it means that there is scope for improvement. It means that there exists an action which is better than the policy's default behavior at that state. And if the advantages are positive for all the states, it means that the performance of my new policy is indeed better than the performance of my old policy. So, this is quite similar to the policy iteration step that we did in dynamic programming. The only difference is that at that time we had not introduced the terminology of advantage functions. Okay, so now we have this. So n of pi old does not depend on uh, the parameter theta because it is fixed. So this is already known to us. We know the performance measure of the old policy. So we ignore this in the maximization function and we only consider this. We only consider the second term because the second term is the one that we want to maximize. The first term is anyways a constant. So it turns out that we want to maximize this expression. Now we are going to do two manipulations to simplify this expression, and at the end of it we are going to get something which we have already seen before. So it will be like visiting an old friend. So let's see. The above expression means something simple. It means that find a policy pi nu that on average prefers actions which have a higher advantage, which intuitively makes sense because if the advantage is higher for all the states, it means that there is a scope for improvement compared to the policy's default behavior, and the new policy can be guaranteed to be better than the old policy. The constraint says that don't let the new policy deviate too much from the old one. Okay, so now we are going to rewrite the objective function in a simpler way, and for that we have to first understand the following basic concepts in probability. The first concept is that of expected value. If we have a random variable x, each with a possible outcome x and a probability p of x, then the expected value of this random variable can be written as x into p of x. Imagine you roll a dice and you ask what is the expected value if I roll a dice. So each possible outcome there is 1 by 6 or 1, 2, 3, 4, 5, 6. So the expected value is going to be 1 by 6 into 1 plus 1 by 6 into 2 plus dot dot dot. This is how you calculate the expected value of a random variable. Now, if we replace this x by f of x and ask the question, what is the expected value of f of x? The only thing we do is we replace this x with f of x, and the expression becomes p of x into f of x is equal to the expected value of f of x. So, this is the fundamental uh, expression which helps us calculate the expected value of a random variable and any function of a random variable. Essentially, you take the function and you multiply it by the probability of the random variable itself. So p of x times f of x. Now, if you consider this expression, rho old of s into y of s. So this is rho old of s is a probability distribution. Remember how we had got this? Uh, this was for every state S0, S1, you had the probability of the agent visiting that state. So this is nothing but a probability distribution uh, across all the states. And you are multiplying it by a function y of s. So this looks quite similar to this expression with p of x being rho old of x and f of x being y of s. So this expression can be written as expected value of y of s. And now we look at our expression, the objective function that we have to maximize. So here this becomes y of s. This is y of s, and we remove this summation out and we replace this by expected value of y of s. So expected value of whatever comes inside, and this expected value is over all the states which are sampled from the state space. So now we have replaced this expression into a simpler expression where we do not have the state visitation frequency anymore, but we have replaced that by an expectation performed over all the states which the agent is likely to visit. Now we will do another uh, simplification. We have now reached here, but we want to make it even more simpler. And the way we do that is as follows. So if you want to maximize x plus c, where c is a constant, then we can remove c from the objective function. We in fact did that initially when we removed uh, n of pi old. So here now you can replace the advantage by q of pi old minus v pi, which is the action value function minus the state value function. This simply comes from the definition of the advantage function. And this the second term is a constant because it only depends on the old policy. It does not depend on the new policy. Whereas the first term, it has this action also inside it. So since the action is going to be sampled from the new policy, the first term is dependent on the new policy, so we cannot remove that term. So then our objective function becomes like this. Okay, but now the question is, can we make it even more simpler? Can we try to see if we can get it to an expression where we are familiar with? What is the expression we are familiar with? Remember, the vanilla policy gradient equation looks something like this. If you look at this expression, this is what we are familiar with, where we know that the gradient of the performance measure is equal to expected value of q of pi s comma a multiplied by grad pi divided by pi. So we are used to this expression, and this is the gradient of the performance measure. So can we somehow modify this expression so that we start to get something like this? Now remember, this is not a gradient. This is just a performance measure. So uh, after taking gradient of that, we should get something like this. Right now, if you take a gradient of this, you will get grad of pi new into q pi old, but there will nothing. There will be nothing in the denominator. So what transformation can we do to make this expression resemble the expression of the gradient of the performance measure that we are used to? So let's see. So this brings us to another concept in probability, which is called as importance sampling. Now let's say that okay, this is the formula for expected value of f of x that we have, but let's say it's difficult to sample from x. We do not know how to sample from x, so we cannot understand the value of p of x. And this is in fact something which is encountered in a lot of problems, uh, which is also encountered here. Since let's say we do not know how to sample from all of these actions under the new policy, we are not able to evaluate this expression. So what people do is that they say that okay, fine, even if you are not able to sample from x, you take the sample from another distribution, which is q of x, which is easier to obtain as compared to p of x. And then what you do is, so now uh, this is what we want. We want the expected value of f of x with x being sampled as per the probability distribution p of x, but this is not available with us. So we do a small manipulation. We divide by q of x and multiply by q of x. And this further simplifies to an expectation over q of x. But inside now, along with f of x, you have p of x divided by q of x. So this is the expression that allows us to evaluate the expectation of f of x under p of x by sampling from q of x. So this is called as importance sampling. We are going to understand this in a better way right now by taking a simple example. Let's say you have this distribution p of x, which is given in red, and we are interested to find the expected value of x under this distribution, which seems to be around 3. Now the question is that it is difficult to sample from p of x, and you don't know how to sample from p of x, so you are not able to calculate the expected value. So let's say I tell you that okay, don't sample from p of x. There is this another probability distribution q of x, which will let you to sample from q of x. So you can confidently sample from q of x. So okay, I say let me do that. But the expected value when I sample from q of x would be around 6. So that would be a problem, right? So then what I will do is I will sample from q of x and I will multiply each sample by p of x divided by q of x. And this will guarantee that I will get an expected value of 3 which I want. And the reason is that since you are multiplying by p of x divided by q of x, every sample is going to be multiplied by that same amount. So the mean also, the mean here is 6, and you multiply it by the mean of p of x divided by mean of q of x, so you get 3 finally. So essentially what you are doing over here is that we give more importance to x which has a higher value of p of x and less importance to x which has a higher value of q of x. That is why it is called as importance sampling. And after importance sampling, the expected value, we get the correct expected value without sampling from the original distribution p of x. Now this is exactly what this formula tells you. This formula tells you that okay, Rajat, you want to calculate the expected value by sampling from p of x, but that is not available. So you sample from q of x and you multiply the function by p of x divided by q of x, and you will get your original expected value. So now we are going to do something similar. Since we cannot sample this action value from the original distribution, we are going to say that I am going to sample from a different distribution which is called Q. And then after I do this, I have to multiply by P of x by Q of x, which is exactly what I am doing over here, where this is P of x and this is Q of x. So Q is the distribution which is easier to sample from. So now I have got my expression, and it looks like this. I want to maximize the expectation of pi new divided by q times q pi old s comma a. The question which all of you might be having is what is this small q? And then what people do is that people usually use the old policy as q because it's easier to sample from the old policy. I cannot sample the actions from the new policy, so I will end up sampling the actions from the old policy itself. So finally we have this objective function, and compare and contrast that with the grad j of theta expression that we have for vanilla policy gradient. It looks like this: expectation of grad pi divided by pi q pi s comma a, and the expectation is over pi. So now this is the gradient of the performance measure. If you take the gradient of this expression, you will get something which looks very similar to this. So now it would appear that why did I do all these things? Why did I calculate a surrogate objective function? I uh, calculated some, or I did some probability manipulations and finally got to this expression. Whereas In hindsight, you could have directly looked at this expression and said, okay, fine, if I write something like this and take a derivative, it will look similar to this. The main problem, I think, why this was difficult to write in the first place is that here you are dealing with pi new and pi old. So it is some sort of iteration over the old policy, whereas here you have a single pi, and to transition from a single pi to pi old and pi new is not straightforward. It involves certain nuances which we have discussed in detail in this lecture and last lecture. So even though right now you look at this and you say this is this is very simple, Rajat. I could have obtained this directly from policy gradients. It's not very simple, because how would you get from this expression directly to this, where you have pi new and pi old? Now, I want all of you to note that people sometimes replace this q value with an advantage value, a pi of s comma a. Both are used interchangeably. Remember, there is a constant which separates the two, so it doesn't make a difference in the objective function. So this expression is something which I want all of you to note down and remember, because it's going to be important for us when we look at PPO objective and subsequently the GRPO objective function as well. Now, okay, now I discuss about the gradient of this performance measure, which is exactly same as the gradient that we get using vanilla policy gradient. Now that we have simplified the objective function, let's try to understand how can we calculate, uh, how can we solve this constraint optimization problem, and how do people solve the TRPO constraint optimization problem. This gradient, we'll call this gradient as G. Okay, so we will replace this terminologies pi new and pi old by pi theta and pi theta old, where theta refers to the new policy and theta old refers to the old policy. The reason we do this is because we assume that the policy is parameterized in terms of theta. So pi new becomes pi theta and pi old becomes pi theta old, where theta old are, you can consider them to be the parameters of the parameterized policy, the old parameters. So we want to maximize this, which we call as y. Now, let's try to see what people do to solve this. What people generally do is that, since we know that pi theta is not going to differ that much from pi theta old, people use a Taylor series approximation for this expression. Now, what does a Taylor series approximation look like? Taylor series says that you can write a function y of theta as y of theta 0 plus theta minus theta 0 into the derivative at theta 0 plus theta minus theta 0 square by 2 into the double derivative, etc. So the series goes on. And if theta doesn't deviate that much from theta 0, then the first order approximation is good enough to approximate the entire function. Let's take a simple example. If we consider sine x, which is the function here, and we consider theta 0 to be 0, then we can use the Taylor series to write sine x as sine of 0 plus x minus 0 into cos of 0, which is x. So we use a linear function, which is x, to approximate sine of x, which performs very good up to this limit. But the moment x deviates from 0 that much, it does not perform good. So Taylor series offers a very nice way to uh, approximate functions who do not deviate that much from the base point. So here the base point I considered was 0. And there is a very simple intuition for this. What you do is you take the base point, you calculate the tangent at the base point, and then that becomes your function. Even though this looks a bit mathematical, all you are doing is uh, calculating a tangent to the true function, and then that becomes your first order approximation. Now we are going to do something very similar here, because we know that pi theta does not deviate that much from pi theta old. So we write our function as f of theta is equal to f of theta old plus theta minus theta old into grad of f theta, where f theta is this expression which is our objective function. Now f of theta old is, this is 1 anyways, so it will only, okay, so this is a constant because the first term becomes 1 for f of theta old. If you substitute pi new old by pi old, so if you substitute theta equal to theta old, pi new will become pi old, and this expression will become 1. So you will get this as the first term. And as the second term, you will get theta minus theta naught times g, which we have already looked at before. So this is a constant, it does not depend on theta. So all we need to do is we have to maximize this expression, g times theta minus theta old, where g is given by an expression which looks very similar to the policy gradient expression. So this is why I said at the beginning that when we reach towards the end of this lecture and look at how the constraint optimization problem is solved, it will look quite similar to the expressions that we had obtained before in the vanilla policy gradient lectures. Now, what to do about the constraint? Well, people also expand the KL divergence using Taylor series, and it can be expanded like this. So again, the base you consider as theta old, and this is the first order and second order. Now, what is the value of this KL divergence of theta old, comma theta old? This is zero because you are considering the same probability distributions. It turns out that this is also zero, which I'll not be covering in this lecture. So the only thing you have is you have a quadratic approximation to the to the uh, KL divergence approximation. So this is the KL divergence approximation, and here you have this term which says grad square dkl max, which is called as the Fisher inversion matrix, which is denoted by A. So the final expressions are given by this. Maximize g into theta minus theta old, there should, yeah, theta minus theta old subject to half of theta minus theta old transpose into the Fisher information matrix into theta minus theta old less than delta. Now, this is something whose solution is given by this. This can be solved and the solution is can be obtained. The main problem with this formulation is that calculating the inverse of this Fisher information matrix is not straightforward. And people use a technique called conjugate gradients to calculate this inverse, but it is a tedious step. And this is one of the drawbacks of trust region policy optimization, that when you reach towards the end, you get a matrix whose inverse is hard to calculate, even though the conjugate gradient method exists and it simplifies this calculation to some extent. Uh, okay, so now to satisfy the KL constraint properly, one factor is added which is called as alpha j over here. So this is the final expression that we get, which solves the constraint optimization problem given by TRPO. One thing you should note is that A inverse here is difficult to calculate, and that's why from TRPO people have gradually moved on to PPO, because PPO does not require us to calculate the inverse of this matrix, which is difficult to calculate. To summarize, TRPO can be summarized into four simple steps. First is to calculate the surrogate objective function, which is always less than the true objective function and matches the objective function at one point, which is given by this L pi pi dash, which is exactly same as the true objective function, but the state distribution is as per the old policy. And the second term is the KL divergence of the old policy and the new policy. Then what you do is that you separate the second term from the objective function and you add it as a constraint, which becomes a trust region. this does not allow the policy to deviate that much from the old policy, then you simplify your objective function using probability manipulations and Taylor series approximation to get these two equations, equation 1 subject to equation 2, where g is nothing but the gradient which we get from our vanilla policy gradient step as well. The only difference is that we have pi new and pi old here instead of just pi, but it looks exactly the same as vanilla policy gradient. And it is subject to this constraint where A is given by the Fisher information matrix, whose inverse is hard to calculate. And actually, this was the last step. In between, I missed to uh, focus on this step, which is the objective function that we get, which we have to maximize. And only after using Taylor series approximation, we can get these two equations, which are noted down in the fourth box. So this is step 1, this is step 2, this is step 3, and this is step 4. This completes our discussion about trust region policy optimization. These two lectures on TRPO are the bedrock of what is to come later, and all the advancements in reinforcement learning applied to large language models that have taken place post TRPO has been tremendous. So, this paper came out in 2015 and it has played a phenomenal role in the advancement of reinforcement learning algorithms applied to modern settings, especially to large language models. And now, in the next lectures, we will move on to how RL is applied to large language models exactly, and we'll eventually cover TPO and GRPO, which is used in DeepSeek. Thank you so much, everyone, and I will look forward to the next lecture.